And my today's session is based upon, the first session is based upon the discussion on inverse probability. Okay, inverse probability is a kind of probability which is associated to conditional probability in some sense. So to know inverse probability, you have to know what conditional probability is. I will definitely do some kind of board works later, but whatever is there in front of the screen, just concentrate on that and listen to me what I'm saying. I'm trying to explain the things in a decent way so that you shouldn't miss any such points. And after the class, once you get my videos of the morning and these sessions, everything will be clear to you. By 27th, as I said, I'm going to take the examination CA1, and CA1's syllabus will be based upon what I teach till tomorrow. Okay. So base theorem is, as you can see, I have written here case 1, case 2, and case 3. Case 2, this part hasn't been colored. Okay, I sometimes miss these things. Case 1, case 2, and below that we have case 3. Now, let me read the statement of the Bayes theorem. Bayes theorem is the theorem of inverse probability. Okay, and it is associated with conditional probability. So what does it say? It says that let capital A be any event. Remember the definition of event. Event is the subset of a sample space which is contained in a Boolean algebra which we have constructed, and a probability measure you have defined on that. Okay, so let capital A be an event that is a subset and it is a part of a Boolean algebra, and capital B is a sub-event of capital A. So you know, if B is a subset of A or B is a sub-event of A, probability of B is less than probability of A. I've proved this result in the last session with you. A Bayes theorem, which is also known as the theorem of inverse probability, goes like this. Now, first of all, you see that I want to find the conditional probability of the event A given that the event B has already happened. Okay, I defined conditional probability in the morning. In conditional probability, what happens is that when you are given a sample space and an event, and you want to find the probability of that event, given that the sample space is in your hand, then actually, when we write probability of A as cardinality of A by cardinality of the sample space, actually we are considering that the condition is that we have the sample space with us. But sometimes, depending upon the situation, what happens, we have to minimize the size of the sample space. We have to squeeze the sample space. Then, depending upon the new sample space which we construct, we find the conditional probability of some event. Okay, original sample space is not considered. A new sample space is considered, which is a squeezed version of the original sample space. And in that way, we try to increase the probability of getting the event. I explained these things in the morning class. You will get to see in my video. Now, the conditional probability of the event A, given that event B has happened, goes by the definition that probability that both the events capital A and capital B has occurred simultaneously. Simultaneous occurrence of the events A and B, we denote this by A intersection B. A and B are happening simultaneously. So probability of the simultaneous occurrence of the events capital A and capital B is divided by probability of the event capital B, because event capital B has happened before you are interested in event capital A. So this first line which is written over here is the conditional probability. It is not the inverse probability. I have just used the definition of conditional probability. Okay, there is one condition that you have to take care of is that the event B's probability should not be equal to 0. That means you shouldn't deal with kind of impossible events. Okay, if probability of B is 0, then in that case, conditional probability has no meaning in. Now, after that, I have introduced another line. Now, suppose somehow I know that conditional probability of the event B, given that event A has happened. Okay, now I can write probability of the simultaneous occurrence of the events capital A and capital B as this: probability of B given A into probability of PA, probability PA. Why is it so? If you have pen and paper in front of you, you can do a bit rough work, that you see that if this is the definition of the conditional probability, I'm saying that this is the definition of the conditional probability. Now, with respect to this definition, try to find out what you get when you write probability of B given A. In that case, you will be getting probability of A intersection B by probability of A, because A had happened there first. So probability of A intersection B can be written as the product of probability of B given A into probability of A. And that product is getting divided by probability of B. Now, what is happening? That when you are interested in finding the probability of an event with respect to the occurrence of a given, with respect to the occurrence of another event, and you are using the inverse of that over here. So when you are interested in finding probability of A given B, you are using the probability of B given A. And therefore, this probability law is called the inverse probability law. So in the first line, I have just written the conditional probability. In the numerator, I have used the conditional probability. But if you want to look at this entire picture, if you take this particular portion of the left-hand side and that portion all together on the right-hand side, you see that this probability is the inverse of that probability. And therefore, this theorem is called the theorem of inverse probability, and also it is known as Bayes theorem. So it happened, this is the statement of the Bayes theorem when there are only two events. Now, if you want to generalize it further, you can do it in such a way that suppose capital B and capital A and capital B be two mutually disjoint and exhaustive events. Now I shall explain what do we mean by mutually disjoint events and exhaustive events, okay, when I'll do the board work. So let capital A and capital B be any two mutually disjoint and exhaustive events, and capital C, suppose, is the event sub-event of the union of the events capital A and capital B. Okay, then in that case, if you are interested in finding probability of A, given that C has occurred on already, first of all, I am using the definition of the conditional probability. So probability of A given C will simply be equal to probability of the simultaneous occurrence of A and C divided by probability of C. Now, as I said, this probability of the simultaneous occurrence of the events can also be written in another way as probability of C given A multiplied by probability of A. So I have written here in the numerator, I have again used the definition of conditional probability. I'm talking about the numerator part only. And in the denominator part, I have written something, as you can see, which is probability of C given A multiplied by probability of A plus probability of C given B multiplied by probability of B. How do we get it? I'm going to explain. Okay. So now in the previous case one, this was the denominator. In case two, where C is a sub-event of A and B, A union B, the denominator has changed. So it is this is called the generalized version of this is the further generalization of the Bayes theorem when two events, mutually disjoint events, capital A and capital B are considered, and one sub-event, which is the sub-event of union of the two mutually disjoint events are considered. This is the expression. And lastly, in case three, I have generalized the scenario, and this is the formula. So I'm just reading this formula out. Let capital E1, capital E2, capital En be small n number of mutually disjoint and exhaustive events. I'll ask all of you to write this particular statement, case 3, in your copy, because whenever I'll be doing the board work, the statement will be in front of you, and you will be able to correlate what I do with the statement. So let capital E1, capital E2, and capital En be n mutually disjoint and exhaustive events, and capital A be any sub-event of union I goes from 1 to n EI. This expression means E1 union E2 union ... union En. So in short, it is written as union over I goes from 1 to n EI. So A is the sub-event of that. Then Bayes' theorem states probability of EI given A. This should be equal to probability of A given EI into probability of EI divided by I. You see carefully, the numerator part has been written over here, preceded by a summation sign. You don't have to remember the expression. You just can derive the entire thing from the definite structure of the conditional probability. Look at the numerator part and the denominator part. Only difference is that in the numerator part, summation sign is not there. In the denominator part, summation sign is there. And here it is written probability of EI given A, which is true for all I. That means if you want to find out probability of E1 given A, then you can use this. If you want to find out probability of E2 given A, you can use this. If you want to find out probability of En given A, then you can use it. So you can say that case 3 is further generalization of case 2. And this can also be called the generalized version or generalized statement of the theorem of inverse probability. So first of all, in the board work, I'm going to prove this Bayes theorem. And once I prove it, everything will be clear to you what is happening over here. Don't try to memorize it. Okay, just memorize the definition of the conditional probability. So I'm stopping this share and I'm moving on to the board, moving on to do some kind of board work. Okay, I hope that you are able to see my screen. So first of all, I have to talk about what we mean by mutually disjoint events and exhaustive events. Let us first of all construct the Boolean algebra. Suppose this entire set I'm drawing, this is my Boolean algebra. It's this figure which I've drawn. It's the collection of different sub-events of some sample space. Okay. Now let us draw this. Let us draw the sub-events. Let us draw the events over here. So suppose this event is E1. Suppose this event is E2, and so on. And suppose, let me draw a few more. Suppose this is the event EM, and suppose this event is En. So in the Boolean algebra B, there are small n number of sub-events of some sample space. Okay, and here M, remember here M is less than n. Okay, now why am I writing this? Because otherwise you may think that why I'm not considering there are M events. I'm considering there are n events according to the statement. Now, first question is, what is this sample space? Where is that sample space? Is this sample space available inside this Boolean algebra? Because you know that sample space is the collection of all possible outcomes. So it has to be a part of the Boolean algebra. Here the sample space are like this. If I denote the sample space by capital S, it is nothing but the union of these sub-events. If you take the union of these events, this is nothing but your sample space. So in these blank portions where no circles are present, actually nothing is there present. Okay, only you consider these individual circles, you take their union, you get the entire sample space. So obviously from the figure, it is clear that the entire sample space is contained inside the Boolean algebra. And on the Boolean algebra, now I have defined a probability measure, capital P. A probability measure, capital P, is now defined on the Boolean algebra. Okay. Now, when I am writing, carefully listen to me. When I am writing that this sample space is nothing but the union of these sub-events, and no other sub-events apart from this are present inside the Boolean algebra, this means that these events, these sub-events, capital E1, E2, En, are exhaustive. When in the statement it is written the events are exhaustive, so that means their union is giving you the total sample space. Okay, we have considered all the possible sub events. No other events are left. Okay. What do we mean by mutually disjointness? Now, by mutually disjoint events, mutually exclusive event is that, remember, okay, let me write it for your better understanding. Mutually exclusive, this word means actually synonymous with disjoint. Okay, this is equivalent to the word disjoint. So whenever I say that capital A and capital B are mutually exclusive, that means capital A and capital B are disjoint. That means capital A intersection capital B is equal to 5. Okay, but here it is written mutually disjoint. Okay, what do we mean by that? By mutually disjoint, what do we mean? It means that if we choose any number of events from this Boolean algebra, then they are mutually exclusive. Or disjoint. Okay, that means, that is, suppose you are choosing capital A, capital E1 and capital E10, suppose, then capital E1 intersection capital E10 is equal to 5. Suppose you are choosing capital E n minus 1, E n plus 2, sorry, not n plus 2, n minus m, and suppose you are choosing E1. If you choose like that, then this sets E n minus 1, E n minus m, E1, they are mutually exclusive. They are disjoint. If you consider all the elements, all the sub-events together, okay, so if you take E1 intersection E2 intersection ... intersection En, they are mutually exclusive. So any pair or any triplet or anything, any number of events you choose from this set, they are mutually exclusive. Then these events are called mutually disjoint events, which means that the events E1, E2, ... En are mutually disjoint events. That's why I have drawn this figure like this. Okay. Now let us consider a portion of the E1. Suppose this is the portion of the E1 I'm considering. Let us shade this portion. Okay, let us take a portion from this set E2. I'm considering this portion. Let us consider this portion from, and let us consider this portion like this. Okay, now you can name these portions like say for example, this portion is named as x1, this portion is named as x2, this portion is named as m, this portion is named as xn, like this for the time being. Now if I take the union of these portions, x1 union x2 dot 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 union xn, then that is your capital A. This is called your capital A. Okay, so now you see what is written. Actually what we are getting, this is just a rough work I have done for your understanding. Now in the statement it is written that it is given capital A is the sub-event of union I goes from 1 to n ei. That is, mathematically you can write A is a subset of E1 union E2 union dot 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 En. Okay, so when we take these unions of x1 x2 xn, this union is taken, that is nothing but your A. Now obviously you see from the figure it is clear that A in this x1, which I name as x1, this x1 is nothing but this x I'm writing over here. This x1 is nothing but, this is the rough work I'm doing. This x1 is nothing but your A intersection E1. This x2 is nothing but your A intersection E2. And your xn is nothing but your A intersection En. Okay, so from figure it is clear that it is clear that this set capital A, this sub-event capital A can be expressed as union of these sets, these events. So I can express A to be A intersection E1 union A intersection E2 union dot 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 union A intersection En. Why can I write this? Because A is the sub-event of the union. This implies probability of A. If I apply probability, then we will get probability of A intersection E1 union A intersection E2 union dot 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 union A intersection En. And from this we get probability of A. Now you see all these sets, A intersection E1, A intersection E2, A intersection En, Em, A intersection En, all these sets are what? They are disjoint. They are mutually disjoint, of course, but they're also mutually exclusive. So for mutually exclusive events, we know that probability measured is finitely additive on the Boolean algebra. So we can write it as probability of A to be probability of A intersection E1 plus probability of A intersection E2 plus probability of A intersection En. Okay. And now this probability of A can be written as, how can I write probability of A? Probability of A can be written as probability of A given E1, A intersection E1 can be written as probability of A given E1 into probability of E1. Why? Because probability of A given E1, if you consider this conditional probability, by definition, it is probability of A intersection E1 by probability of E1, and so on, and so on. Okay, so I can write it in this manner, plus probability of A intersection E2, A can be written as probability of A given E2 into probability of E2 plus dot 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 probability of A intersection En can be written as probability of A given En into probability of En. Okay. And if you don't want to write everything, you can put a summation over there. Summation I goes from 1 to n, probability of A given EI into probability of EI. So we have got this. This is number one. So we have got this from the definition of conditional probability. We are interested, according to the statement, look at the statement of the problem. We are interested in finding probability of an event E1 with given that the event capital A, the sub event has already happened. Okay, so what about this? So I'm moving on to the next page. Okay, but before that, let me write something over here. We have space. We are interested in finding, we are interested in finding the probability of the event EI given that the sub event A has happened already. Okay, so and it is, we are interested in finding such probability for all I. So in that case, mathematically we can write it as, therefore we want to find probability of EI given A for all I. Okay, now probability of EI given A, by the definition of the conditional probability, this can be written as probability of EI intersection A, or you can write it as yeah, okay, no problem, you can write in this manner, probability of EI intersection A divided by PA. No problem. I have used the definition of conditional probability now. In the above part, I mean the numerator portion, you can again break this in terms of conditional probability. So you can write it as probability of A given EI. Don't break it in terms of probability of EI given A. Otherwise, on the left hand side and on the right hand side, you are going to get the same thing. Nothing dissimilar will come. So probability of A given EI into probability of EI by probability of A. Now using 1 in equation 2, we get ultimately that probability of EI given A is actually equal to probability of A given EI into probability of EI divided by summation I goes from 1 to n, probability of A given EI into probability of EI, and which proves the Bayes theorem generalized version. I hope you have understood. So I'm again showing what I have done over here. I have constructed a Boolean algebra where several sub-events have been considered. All these sub-events are in such a manner, are designed in such a manner that if you consider any 2 events or any 3 events or any 4 events, they are disjoint. So these sub-events are actually mutually disjoint sub-events. And if you combine all the events together with the help of union, then you actually get your sample space, which is contained in the Boolean algebra itself. After that, what you are considering, you are designing the event, sub-event capital A in a special way. You are taking some portions from these sub-events E1 and E2 and EM and EN. Now these sub-events, initially I'm writing those sub-events as X1, X2, XM, XN. It is given in the question that your sub-event capital A is actually the union of this sample space. So since A is the sub-event of this union, now A can be expressed as A intersection E1 union A intersection E2 union ... A intersection En. So whatever I actually used, the notation I used for this shaded region, shaded portions, that is x1, x2, xm, xn, these are nothing but your events. A intersection E1 stands for x1, A intersection E2 stands for x2, A intersection En stands for xn. I'm defining probability measure on the Boolean algebra and applying all the probability measure on all the sub events. So we get probability of A as probability of the entire thing. Now we know that since probability measure defined on the Boolean algebra is finitely additive and for the mutually exclusive events, and since these events A intersection EIs are mutually exclusive, so probability of A becomes the sum of these individual probabilities. Now, by the definition of conditional probability and assuming that E1 has happened before A, we are rewriting this probability of simultaneous occurrence of A and E1 as this probability of A by E1 into probability of E1. I am using the definition of conditional probability. All the probabilities have been written in this manner, and I can summarize the entire thing by putting a summation sign before that. So we have found our probability of A. Now, if someone is interested in the reverse thing, that if someone is interested that, okay, I'm interested in finding the probability of each of these events, EIs, given that the sub-event has already happened. So what he is doing, he is writing this as probability of EI given A. And again, he is applying the definition of conditional probability, which is probability of EI intersection A by probability of A. Probability of EI intersection A again can be written by the definition of conditional probability as probability of A given EI into probability of EI by probability of A, and then nothing is left with. We want to substitute the expression obtained in equation 1, which we have already found. And by putting this, we are getting the generalized version of the Bayes theorem. And thus it is proved. I think there is those who are new to this particular probability theory, probably they are finding a little bit of difficulties in understanding. But if you go through these theorems again and again, so you will definitely, I'm doing nothing. No rigorous mathematics is being done. I am just putting one ball from this basket to that basket, and then again from that basket to this basket, and then again from this basket to that. But same thing is being repeated to get the ultimate expression. So it is not at all actually difficult. Okay. So I'm stopping the share. So thus we have proved this particular result. And in this note, you can see that I have also shown these by drawing these figures, that what is happening. Probably you didn't understand why I drew these figures like that. So I have shown these things in this manner. Okay. So I think I must stop here right now. In the next session, I'm going to continue with one or two problems on Bayes theorem and theorem of inverse probability. Okay, but if the time is only 2 minutes 19 seconds is left, and I ask all of you to join in the next session and the last session of today's class, and then I'm going to explain one or two problems on the theorem of inverse probability, and also I can explain one or two problems on conditional probability. Okay, so I'm stopping here right now.